that and I'll give you a couple of days time for you to upload the assignment. Okay. Now, what we did was like we looked at the construction of the centrifugal pump yesterday. Then we looked at different pressure rates associated with the centrifugal pump. So one being the suction head, the delivery head. Then we had the frictional losses or frictional heads we call it on the suction side as well as on the delivery side. Then we looked at the exit loss, that is the delivery. There is some amount of kinetic energy which will be lost in the form of V square by 2G. It's that particular thing. So that we call it as an exit loss. And then we defined what is called as an Euler rate. And then we ended up with your manometric rate. Today, we'll try to look into what are the different efficiencies associated with your centrifugal pump. Okay, efficiencies associated with centrifugal pump. Okay, now what type of machine is a centrifugal pump? Centrifugal pump is a power absorbing machine. So in that case, I am going to supply the energy to the shaft. See, some amount of energy is applied to the shaft, that is taken as the energy supplied to the shaft. This is from the motor. Then there will be some amount of losses. If I take one box and in that I'm going to put a what are the losses? Mechanical losses. So here I may call it as mechanical losses. Then there will be some amount of energy available at the rotor. Okay, energy available at the rotor. Okay, then see, from the rotor it has to reach the fluid actually. So in between what I have the blades, all those things and all. So blades, and there can be some kind of a casing, all those things are there, where there can be some amount of loss in the form of leakage or in the form of friction between your blades, all those things. And I call that as hydraulic losses. Okay. Then, so at the end, we have the energy available at the fluid. That is the energy that is transferred to the fluid. Okay, if I call this as 1, this as 2, and this as 3. Okay, now let us try to define the efficiencies. So if I want to define the efficiency of mechanical, that is mechanical efficiency, okay, the first thing is mechanical efficiency. So mechanical efficiency, it is eta mechanical. So what it is actually, see, efficiency is nothing but, it is nothing but output to input. Okay, now if I define it, your mechanical efficiency is nothing but, it is the energy available at the rotor. Okay, energy available at the rotor or impeller, whatever is. I think few books they call instead of rotor, they call it as impeller, doesn't matter, it's the same. To energy that is supplied to the shaft. Okay, energy supplied to the shaft. I think few books actually instead of energy, they use power. Okay, instead of energy, they use power, so that's also fine. So if I try to put it over, it is 2 divided by 1. Now, see, we can't have power available in the impeller and power available in the shaft, both can't be same. So in that case, this number should be always less than 1. That is, your mechanical efficiency is always a number less than 1. That is, your mechanical efficiency is between 0 and 1. Most of the books are this thing, we try to take this number between 0.85 to 0.95. That means a new machine will have a higher mechanical efficiency compared to old machines. As the machine gets older and older, so this mechanical efficiency will drop because of the lot of mechanical frictions. Okay, bearing losses, all those things, or shaft, maybe rubbing, all those things over a period of time. Now the second efficiency. So second efficiency is actually it is and few books call so manometric efficiency. So it's a name, it's the other name, manometric efficiency or hydraulic efficiency. What it is actually, it is the energy available with the fluid, that is energy. I think few books they call this as head also. Okay, head available with the fluid or at the fluid, that is energy that is transferred to the fluid to the energy available at the rotor. Okay, energy or head available at the rotor. So if I try to write in terms of what I have defined, it is actually, it is 3 divided by 2. This is your hydraulic efficiency. Okay. Now, what about this one? This is also less than 1. So your hydraulic efficiency will be also a number between 0 and 1. Okay. Now, energy available with the fluid. Okay. What it is actually, if you go back and see, this is the energy available with the fluid. That is your manometric head. What is the energy available at the rotor? This is your Euler head. And the hydraulic efficiency can also be written as, so hydraulic efficiency can also be written as, if the ratio of manometric head, that is your actual head, okay, divided by your theoretical head or Euler head, or what is the energy available at your rotor, that is HE. That means few books they call this as HM by HE. Now what is the expression for HM? I can leave with it. What is your HE? I can write in terms of mathematical, I can write it as HM divided by VW2 into U2 minus VW1 into U1 by G. Suppose if VW1 is 0, then I can write this as HM divided by VW2 into U2 by G if VW1 is equal to 0. Or the same expression I can write it as G, if I take it to the top numerator, this will be G into HM into VW2 into U2 minus VW1 into U1, or I can write it as G into HM divided by VW2 into U2. So if VW1 is equal to 0. And what will be this hydraulic efficiency? See, even this number is between 0.85 to 0.95 or 0.9 roughly. Your hydraulic efficiency will be higher when I have a new pump, and this number is going to reduce with usage. Okay, this is about your hydraulic efficiency. Then I have the third efficiency. Okay, then I have the third efficiency. What is the third efficiency? That is your efficiency. The third one, it is your volumetric efficiency. Volumetric efficiency. What is it actually? See, I could see that there is a little bit of fluid you are exiting the pump, but the fluid that is entering is little more. The fluid entering is more, but exiting is less. Okay, that is your volumetric efficiency. I can write it as the mass of volume of the fluid, the volume of the fluid exiting the pump to mass or volume of the fluid entering the pump. Fluid entering the pump. I can write this as m dot by m dot plus delta m. So where delta m is the amount of fluid that is lost. I want to write in terms of discharge, this q by q plus delta q. So more amount of fluid enters your pump, but there is something lost. There is a little bit of between 1. Most of the times this volumetric efficiency, we want this to be between 0.9 to 0.98. Okay, roughly around 0.9 to 0.5 or 0.98 is what we consider when you are designing the pump. Okay, then the last one, your overall efficiency. The overall efficiency, of your pump. Okay, what it is actually? It is the manometric head, or what you can call it as, what is your energy available with the fluid to the energy that is supplied to the shaft. Okay, I can write this as overall as energy of with the fluid energy or power supplied to the energy supplied to the shaft. Okay, so that is nothing but your 3 divided by 1. I think few books they define it as the overall efficiency. They define it as it's a ratio of manometric head to the power input to the shaft. That is power input to the shaft. This is also fine. That is HM divided by P. Okay, and also your overall efficiency is also the product of your mechanical efficiency, your volumetric efficiency, and your hydraulic efficiency. That's why your overall efficiency is always less. Okay, the overall efficiency is always less. So these are the efficiencies associated with your centrifugal pump. The first one being the mechanical efficiency, the hydraulic efficiency, the third one being the volumetric efficiency, and the fourth one being the overall efficiency. These are the definitions going. Okay. One thing we remember. That means here what we try to do is actually when we call that as analysis of centrifugal pump. Analysis of centrifugal. So we are going to analyze this pump for different conditions. The first one is effect of your exit blade angle beta 2. Okay, effect of blade angle. Okay, effect of beta 2 on your head developed. That is your H. Effect of beta 2 on your head. Hope you remember during maybe on centrifugal pump, we had plotted Q versus Q. Okay, we had W versus Q and H versus Q for varying beta 2. That is exit blade angle. Exit blade angle. Okay. Hope you remember we had this expression also. That is W is equal to U square. That is U2 square minus U into cot beta 2, okay, into Q divided by A2. This expression was there. This we have derived. And what we wrote is as a straight line where U2 was taken as P minus U, that is C U2 cot beta 1 U2 square, and C2 was taken as U2 cot beta 2 divided by A2. This is what we took in our centrifugal compressor. Now, even the pump is also very similar to a centrifugal compressor. One thing, the difference is actually, I will try to express in terms of head. So, what I do here, in terms of head, terms of pressure head, I call it as pressure head, or simply Blue Books call it head. I can write H is, what is H actually? H is equal to your W by G. So I can write H is equal to U2 square by G beta 2 Q divided by EA2 into G, or I can write H is equal to C3 minus E4 into Q. Here C3 is equal to U2 square by G and C4 is equal to U2 hot beta 2 divided by A2 into G. The only term what I am trying to add is actually it is a G quantity. I am trying to bring it so that I am going to express in terms of the head quantity. Now, if I try to plot, when I have this kind of an expression, when I try to plot it, what I am going to get actually. So now, so this is what I have. That is discharge of the x-axis and head down the y-axis. This is my discharge and this is your head. So I will be having the beta 2. So this is, I asked you people to plot it. Okay, this is for beta 2 is equal to 90. So I may be having a term beta 2 greater than 90 like this. This is for beta 2 greater than 90. This is what I'm going to get it. So and this discharge start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what is this actually? This is your square by G, which is. So now if you put also, so I will take this expression H equal to your U2 square by G minus U2 into beta 2 by A2 into G and to Q. I will want to fix the value of beta 2. Say for example, beta 2 I will take a value between 0 and 90. I'll check for how the head will. So let me take the speed as 0.25 meters. Some value I'm going to take for a fixed diameter, speed, and a given beta 2 angle. and for varying discharge, I will write this plot. So I can try for three different conditions. Any of beta 2 is equal to 90, the right hand term will definitely become 0, it remains almost constant. So where I want to see this varying quantity is actually only for beta 2 less than 90 and beta 2 greater than 90. I can just put it in an Excel file, all simple, I can write a code and try to verify. So whatever exercise you did for your centrifugal compressor, a similar exercise will be done for your centrifugal pump also. There it was with respect to work, that is specific work W. Here it will be in terms of your head developed or pressure head developed. Okay. Now, so there is one more thing, analysis I told, effect of beta to V. The second thing is actually already been the slip and slip factor. Slip and slip factor. Okay. So slip actually, so I can call that as sigma or something. So slip factor, so you can call that as maybe omega or whatever it may be. Okay. Slip and slip factor. So here we most probably we try to involve with slip factor. That is, the slip is nothing but difference in your whirl velocity difference. Okay. Then your slip factor, that is sigma. Now, only I want to show the exit velocity triangle. Okay. I have this exit velocity triangle, something like this. What will happen? So you have a blade like this. So you have a blade like this. So this is my blade. Okay, this is my blade. And here this is my blade. The fluid will enter like this. So this is my inlet angle. So inlet velocity triangle will be something like this. So let it be VW1 is equal to 0, doesn't matter to me. So I'll be having a inlet velocity, sorry. So my inlet velocity triangle will be something like this. I'm not exactly drawing to the shape or something. So this is my alpha 1, this is my beta 1, okay. This is my ER1, okay. This is rotating in this direction. So this will be my U1, VW1 is equal to 0. This is my V1, which is equal to VF1. This is my inlet velocity triangle. Now, outlet velocity triangle, let me write out my outlet velocity triangle. If I try to draw my outlet velocity triangle, this will be my VR2, okay. Then I can have my VW, so it is my V2, this will be my V2, and so I am trying to draw a bigger velocity triangle so that at the exit my energy level is more, okay. This is my alpha 2, this is my beta 2, the whole is my U2, okay. The whole whatever I have, this is my U2, this is my U2, this is my velocity triangle. Then if I try to draw the components of it, actually this will be my VF2 and this will be my VW2. So this quantity from here to here is my VW2. So this is my exit velocity triangle. Now I told that with the slip what will happen? So because of the slip actually there will be a recirculation like this. The fluid will, instead of going in this particular thing, there is some kind of a circulation at the tip of it. So because of this, what will happen to your velocity triangle? Your velocity, the VW2, what is the VW2 will become smaller. See, your VW2 will become smaller like this. Okay, let me call this as your VW2. So this will be your VW2 dash. And what will happen to your alpha 2 dash? So your alpha 2 dash will increase. Will there be any change in my U2? So what will happen? Your U2 dash will see when this quantity gets reduced, what will happen to your U2. So U2 is almost same. So U2 we can't change it. So what will happen to your U2? So because of this actually, it will go in this direction, and so I'll be getting your U2 will number will remain same. So this is my U2. Okay, your U2 will remain same, but there is this will be my new V2 dash, and this will be my new VR2 dash. See, all other quantities I could see there is a change, because what is U2? U2 is nothing but your pi into D2 into N by 60. Suppose if U2 there is a reduction for the same diameter, there will be reduction in speed. Agree? If the U2 doesn't change, then what will happen? I am going to get a triangle of this particular form. If suppose U2 also changes, then there will be reduction in speed, because a diameter I am not changing. I'm not bothered about what is the changes that is happening with respect to U2, but I'm worried about the changes that is happening with respect to your world velocity. Okay, what is that actually? Slip. What is this slip actually? Slip is nothing but it's a difference between your ideal world velocity to actual world velocity, which I call it as delta VW2. That is happening at the exit. So slip is nothing but change in your world velocity at the exit of your pump or whatever it may be. Okay. What is slip factor? Okay. What is slip factor? Which we have seen. Maybe sigma. It is nothing but it is the ratio of your slip to, that is, slip is nothing but your VW2 minus VW2 dash to its ideal world velocity, or I call it as delta VW2 by VW2. So this is called as your slip. Fine. Now, but what is this number? This number will be less than 1. The slip will reduce your work capacity of that particular pump. Okay. Is there any possibility to minimize the slip? Okay. How to minimize? To minimize the slip in a pump. Okay. What should be done? So, what I have tried with experiment is actually they are trying to make this vane, the vane surface has to be smooth. The vane surface has to be smooth. If you have a rough surface, there is every possibility of this thing happening. Okay. Then try to maintain a streamlined flow. See, to maintaining a streamlined flow in between streamlined flow between the veins, between the blades or veins. Hope you remember in my first class what I told this, we call it as vein congruent flow. If this is my vein, this is one vein, and if I have a similar vein, okay, if I have a similar vein like this, and I do have a blade like this. So what do you mean by vein congruent flow? The vein congruent flow, this is one blade 1, okay, this is a blade 1, this is a blade 2, and between this, how should be my flow? The flow should be like a streamline. See, it should be like this. So the flow should be in a streamlined pattern. These are streamlines. The streamlines. Okay, these are streamlines. If I try to have such a flow, that means there should not be any free circulation. Say, suppose if there is any recirculation like this, that means it is not a vein congruent flow. There should not be any pressure gradients. That is, no pressure gradients here. Say no pressure gradients. To be very precise, I think some of the books they call that as adverse pressure gradient. There should not be any adverse pressure gradient which may lead to formation of small eddies or vortices which will disturb your streamline pattern. Okay, when you have such a thing, that means when you have a complete streamlined flow, we call this as vein congruent flow. There should not be any disturbance of the flow. So this, if I'm able to attain, and you try to maintain this surface, see this surface and this surface as smooth as possible. So when I try to maintain this surface as smooth as possible, the friction between the flowing fluid and your hard surface, that is your solid surface, will come down. We call that as skin friction drag. If this reduces, the possibility of recirculation or possibility of disturbances will come. So it is, you can't just avoid it, but you can minimize it. The slip can be minimized by just doing few things. One is maintaining a very smooth vein surface, the first thing, and the second one is try to maintain a streamlined flow. If I'm able to have these two, then I'll be able to minimize my slip. This is nothing but a loss. I can minimize slip as much as possible. What will happen? This will bring down your head developed. If the slip if the slip is more, then the head developed by the pump will go down. If the slip factor is very, very small, then the head developed by the pump also will increase. Okay, this is about your slip factor. And we have the third quantity. Okay, the third quantity is what we call it as the maximum suction lift. Okay, we call that as maximum suction lift. And some of the books they call this as MSL, maximum suction lift, and it is called as MSL. What it is actually? Okay, suppose, see, we try to get a centrifugal pump from the market. Okay, now I want to install the centrifugal. So when installing, I need some kind of what is called as a center line. Okay, let this be some center line of your centrifugal pump. Okay, now if I want to install this, actually, let me install this particular thing. So this is my impeller. Okay, I have an impeller like this. Okay, I have an impeller. So these are my veins. Just I draw a simple rough sketch of it. Okay, some 5 veins are there. Now to this, actually, I can draw what is called as your casing. Okay, I can draw the casing. This is your casing. So this is a volute type of casing. Here it is increasing. I do have a suction is somewhere to the center actually. The suction something like this. It is connected over here to the center of pipe actually, and can have the. So this will go to the sump and go to the sump, and on the other side I can have delivery. I can have the delivery pipe which is coming over here. This is my delivery pipe. This is where I have a suction. This suction will go to eye of the impeller. Okay. Now, so I have the sump of water somewhere here. Sump of water. So this is my sump. Okay. This is my sump, and I do have a foot wall here. So I do have foot wall, which is like a mesh. It's like a mesh here. This is my simple foot wall, and this is my free surface, water free surface. So it's my sump. Okay, I have water. The foot wall is completely immersed in the water. Okay. Then my datum. If I call this as Z, this is my datum for all your references and all. We take it. This is my datum, and this is my suction pipe. Suction pipe. Connected some. Okay. So what phase of your then see the fluid will start moving in this direction. So if the fluid will start moving in this direction, so at the eye of the impeller, see this is the place where you have minimum pressure. So it is the place where you have minimum pressure. Okay, that is eye of the impeller. We call this as eye of the impeller. This is your eye of the impeller, and this is your center line which passes through your eye of the impeller. Now what will happen? See, once the flow goes in, the fluid is it starts coming in all directions like this. Then it will go up this direction. It will start going in this direction. So this is my delivery pipe. This is my delivery pipe, and if you want, I can have a delivery valve here, and a key pressure housing. I can have a simple construction. I have my now there. What is my suction head actually? If I try to measure from the if I try to measure from your suction surface to the center line, if I try to measure, this is my suction head. Agree? This is my suction head. Now, suction head, if you try to look into it actually, this see, when I try to place this suction head, to where should be my center line? Can this center line HS depends on many things. Can I place my pump? Say I want to pump the water from my sump, which is at say 2 meters or 3 meters from the ground level, to a 3-story building or a 4-story building. If that's the case, where should I have my center line? Whether the center line is, where should I install my pump? My first pump in the second floor, or whether I should install my pump in the third floor. You might have seen this is what most of the people they try to do. See, they will be having a sump in somewhere in the basement. They will be put the centrifugal. Sometimes the pump, a very large pump they will try to put. They will try to put a very large pump, maybe 5 HP, 10 HP pump and all, because this HS requirement increases. Where should I have my center line? Where should I install my pump? That is called as your maximum. What is MSS? Is the maximum height. where should I have my height actually? It is maximum above pump level is very close. See, maximum height, okay, maximum height under which the pump is installed or placed. The pump is above the pump, and this maximum lift. You can't install, see, from the sump is at the somewhere the base, maybe around 8 to 10 meters. So you can't have HS around 10 meters and delivery head meter or 0.5 meters. So I should ensure that this HS has some limit, and this is calculated. Okay, this is calculated based on many things. Okay, I should ensure that whenever I'm trying to have this, not many factors are there. One being your atmospheric pressure. Your atmospheric pressure, what is it actually? If I call PA as atmospheric pressure, what is your atmospheric head actually? HA is equal to PA by G. So rho G, PA by rho G, this is your atmospheric head. Atmospheric head. Now, how to find this actually? How to find this as section 1.1. If I call this as section 2.2. I'm going to apply my Bernoulli's equation between your 1.1 and 2, and I will be able to find this MSL. Okay. And one more critical point here. Okay, I have to ensure. See, I have to ensure what is this pressure here. See, if I call this as minimum pressure at P2, the P2 should not go below your vapor pressure of the fluid. Agree? See that the thing is very important. What is the most critical point here is, while defining your maximum suction lift actually, the P2 is the minimum pressure. I have to ensure that P2 should be greater than your vapor pressure of that particular fluid. What is vapor pressure? So what is this actually? It is the pressure. It is vapor pressure is the pressure at which the fluid, that is the water, the fluid changes its phase. That means the fluid from liquid to vapor is very critical. It never falls below your vapor pressure. So now what I'm going to do, apply your Bernoulli's equation between 1 and 2. So applying Bernoulli's equation. If I try to apply, what is it actually? Have the pressure rho G plus your candidate, that is V1 square by 2G, plus your head, that is we call it as Z1, that is your what is called as your maybe potential head, is equal to E2 square by Z2 square losses in the section 5. That's what I'm doing. This is a simple. I'm trying to write your Bernoulli's equation. That is the sum of the head, kinetic head, and potential head at 1, and the sum of the pressure head, kinetic head, and potential head at 2 is an ideal. But when I come to practical thing, there is something called as the losses, which is your HF in pipe. Now, what is done? So, the fluid is stationary. Agree? When a fluid is stationary, practically these two quantities become me. Then what is your P1? Your P1 here is, see, P1 is equal to your P atmospheric. So I can write this Bernoulli's equation as P1 as PA by rho G is equal to P2 by rho G plus V2 square by 2G plus Z2, okay, plus HFS. Okay. Now, I can write it. I can write H2 is equal to P2 by rho G. Okay. What is your HA? HA is equal to PA by rho G. See, what is your Z2? Z2 is nothing but, see, I can write, what should be my Z2? Rewriting this particular thing, your Z2 is equal to HA minus your H2 minus, okay, V2 square by 2G minus HFS. Okay, so I'm calling that as expression number 2. Now this is critical here. What is Z2? Z2 your maximum suction lift. Just go here. This is your Z2 or your HS, your Z2. Or what should be my maximum suction lift? That is your Z2 is equal to, that is MSL is equal to HA. What is your H2? Your H2 should be vapor. It should be greater than your H vapor. That means I should ensure that this is HV minus your V2 square OG minus HFS. Any given point, MSL is given by this expression, the equation number 3. This will give my maximum suction rate. Just I'm trying to apply the Bernoulli's equation and try to get the expression point. So this is the expression.